Welcome to the deep dive. Ever wondered if, that big marketing push actually did anything? Or if something you've noticed, like maybe more part-time students around, is actually a real trend?
Exactly. And that's where something called hypothesis testing comes in. It's basically a way to use data, actual numbers, to answer those kinds of questions.
Right, so you move beyond just a hunch, yeah. You get actual evidence.
Precisely. They give it like a detective's toolkit, but for data. You start with a question, maybe a suspicion, you gather the evidence, the data, and then you use these statistical tests.
To see if the evidence is strong enough?
Yes, to see if it points strongly in one direction, or if it could just be, random noise.
Okay. So for this deep dive, we've got some examples lined up.
We do. We've pulled them from a really good statistics manual. Lots of real-world scenarios showing hypothesis testing in action.
And you said real world, like what kind of things?
Oh, all sorts. We're talking about job creation numbers in counties, whether dentists are earning more, even things like taste tests for soft drinks. It's quite diverse.
Sounds good. So the aim today is to really get a feel for the logic behind it all, how it helps us tell if a pattern is, real or just chance.
That's the goal. Understand the core idea, see how it works across different situations, and figure out what statistically significant actually means. Where should we start?
How about that job scenario you mentioned?
Okay, perfect. So, scenario 1. Back in 2005, the Department of Economic and Community Development said, on average, counties were creating 450 new jobs.
Okay, 450, that's our baseline, kind of.
Exactly. Then in 2006, they took a small sample, just 5 counties: Bradley, Rhea, Marion, Grundy, Sequatchie.
And what did they find?
The numbers were 410, 480, 407, 428, and 400. So you look at those, and some are lower, ones higher.
Yeah. The average looks like it might be lower than 450.
It does. The question is, based on just these 5, can we say there's been a significant decrease across the board, or could this just be random fluctuation?
Right. So this is where the hypotheses come in, the null and alternative.
Yep. The null hypothesis, H0, we often call it, is usually the status quo idea. Here, it'd be that the average number of jobs is still 450 or maybe even more. No real decrease.
Okay, no change or it went up. And the alternative?
The alternative hypothesis, H1 or HA, is what we're looking for evidence for. In this case, that the average number of jobs has actually gone down, that it's less than 450.
Got it. So what did the math show for those 5 counties?
Well, the average for that sample of 5 comes out to 425 jobs.
Okay. Lower than 450, as we thought.
Lower, yes. And the standard deviation, which measures the spread, was about 32.43. Now, because we have a small sample and we don't know the overall population standard deviation, we use something called a t-test.
A t-test, right.
And that calculation gives us a t-statistic of negative 1.7235.
Negative because the sample average is below the hypothesized average.
Correct. And associated with that t-statistic is a p-value. Here it's about 0.0799, let's say 0.08.
The p-value, that's the important bit, isn't it? Tell us what that 0.08 actually means.
It is key. Think of it this way. If the true average number of jobs was still 450 or more, if the null hypothesis was true, what's the probability we'd get a sample average as low as 425 or even lower just by pure random chance of picking those 5 counties?
And that probability is about 8%.
Around 8%, yes. Now, we usually compare this p-value to a threshold called the significance level, often denoted alpha. A common choice is 5%. Or 0.05.
So our p-value of 0.08 is higher than 0.05.
It is. Since it's higher, we say the result isn't statistically significant at the 5% level. We don't have strong enough evidence to throw out our initial assumption, the null hypothesis.
So even though the sample average was lower, we can't confidently say there's been a real decrease overall. It could just be chance.
Based on this small sample, yes. We fail to reject the null hypothesis. There isn't significant evidence of decrease.
Okay, that makes sense. Sometimes what looks like a change isn't strong enough statistically. What about the dentist's income? That sounds different.
It is. Scenario 2. In 2005, the Bureau of Labor Statistics reported the average dentist income was $110,000 a year.
Okay.
Then in 2006, a larger sample this time, 81 dentists showed an average income of $120,000.
$10,000 higher on average than the sample.
Right. And for this one, let's assume we know the population standard deviation of dentists' incomes is $36,000. That's a key difference from the last example.
Knowing the population standard deviation changes things.
It does. It means we can use a z-test instead of a 2-test. The question here is, has there been a significant increase in the average income?
So the null hypothesis is income is still $110,000 or maybe even less.
Exactly. H0.
Yeah.
Average opens $110,000.
Yeah.
The alternative, what we suspect might be true, is H1. Average $110,000.
And the calculation.
The z-statistic calculation gives us a value of 2.5.
2.5. That sounds further away from 0 than the last one.
It is, and the p-value associated with the z-score of 2.5 for a one-tailed test like this is very small. It's about 0.00062.
0.00062. Okay, that's much smaller than our usual 0.05 cutoff.
Much smaller. So what does that tell us? If the true average income was still $110,000 or less, the chance of randomly picking 81 dentists with an average income as high as $120,000 is only about 0.6%. Very unlikely.
So unlikely that we should probably doubt that initial assumption.
Precisely. Because the p-value, 0.00062, is less than our significance level, 0.05, we reject the null hypothesis.
And conclude.
We conclude that there is strong statistical evidence of a significant increase in the average yearly income of dentists between 2005 and 2006.
Okay, so a small p-value gives us confidence that the change we see is likely real. Makes sense. What about that tire company claim?
Right. Scenario 3. Back to a t-test for this one. A tire company used to say their tires lasted on average 26,000 miles.
Okay.
Now they have new tires, and they're advertising an increased life expectancy. So someone tested 6 of these new tires.
Only 6? That's a small sample again.
Very small. And the mileages they got were 28K, 27K, 25K, 28K, 29K, and 25K.
Mostly above 26,000, but a couple right at or below. Is the advertising legitimate?
That's the question. The null hypothesis would be that the new tires are the same or worse, average 26,000 miles. The alternative is that they are better, average 26,000 miles.
In the sample
For
average.
those 6 tires, the average is 27,000 miles.
So 1,000 miles higher than the old average.
Yes, with a sample standard deviation of about 1,673 miles, the calculated t-statistic is about 1.46. And because Ni 6, we have N119 degrees of freedom.
Okay, T1.46. What's the p-value for that?
The p-value comes out to around 0.1016, or about 10%.
10%, so higher than 5%. But this one mentions a 99% confidence level.
It does. A 99% confidence level means we're using a very strict significance level, alpha equals 0.01. We want to be really sure before we support their claim.
And is a p-value of 0.10 less than 0.01?
Not at all. It's much larger. The manual also mentions the critical t-value you'd need to beat for significance at 1% with 5 degrees of freedom, which is quite high, around 3.36. Our 1.46 doesn't come close.
So we don't reject the null hypothesis here either.
Correct. Even though the sample average was higher, with such a small sample and demanding such high confidence or low significance level, the evidence isn't strong enough. We can't statistically support the company's claim based on this test.
Interesting. The sample size and the confidence level really matter. What's next? Credit balances.
Yep. Scenario 4. A credit company looks at a sample of 81 account balances. The average balance in the sample is $1,200, and the sample standard deviation is $126.
Okay, 81 accounts, average $1,200.
The question is simply, is the true average balance across all their accounts significantly different from $1,150? Not higher or lower specifically, just different.
So this is a two-tailed test. Null hypothesis. The average is $1,150. Alternative. The average is not $1,150.
Exactly. We calculate the t-statistic again. It comes out to about 3.57. With N81, we have 80 degrees of freedom.
3.57 sounds pretty significant. What's the p-value?
It's very small, around 0.00006.
Tiny. Definitely less than 0.05.
Absolutely. So we reject the null hypothesis. The evidence strongly suggests the average account balance for all customers is indeed different from $1,150. Given the sample average was $1,200, it seems significantly higher.
Okay, clear cut. How about that carpet company's delivery promise?
Scenario 5. This company advertises delivery within 15 days.
Sounds optimistic for carpets.
Maybe. They surveyed 49 customers, and the average delivery time for this sample was 16.2 days. Let's assume we know the population standard deviation for delivery times is 5.6 days.
Okay, average 16.2 days, which is longer than their advertised 15 days. So is their ad legit?
That's the test, null hypothesis. Their average time is 15 days or less, including the ad. Alternative, their average time is actually greater than 15 days.
And since we know the population standard deviation, it's a z-test.
It is. The calculated z-statistic is 1.5.
1.5, okay. P-value.
The p-value for this one-tailed test is about 0.067. The manual also notes the critical z-value for a 5% significance level is 1.645.
So our z-statistic of 1.5 is less than the critical 1.645, and the p-value of 0.067 is more than 0.05.
Correct, on both counts. So we fail to reject the null hypothesis. Meaning, even though the sample average was 16.2 days, the evidence isn't strong enough statistically to conclude their true average delivery time is significantly more than 15 days. Based on this data, their advertisement isn't proven false. It's considered legitimate.
Wow, so being slightly over in the sample wasn't enough to sink their claim statistically. Fascinating. What about the factory workers in the training program?
Scenario 6. This one uses a paired t-test, which is interesting. We look at the same 5 workers before and after training.
Okay, comparing each person to themselves.
Exactly. Worker 1 went from 6 units to 9, worker 2, 10 to 12, worker 3, 9 to 10, worker 4, 8 to 11, worker 5, 7 to 9.
Looks like everyone improved.
They did. The question is, was the improvement statistically significant? Did the program work? Null hypothesis. The difference after before is 0 or less. No improvement. Alternative. The difference is positive improvement.
And the test result.
The calculated t-statistic for the differences is quite high, 5.88. With 5 workers, that's 4 degrees of freedom.
And the p-value for that?
Very low, about 0.002.
0.002, way below 0.05.
Absolutely. We reject the null hypothesis. The statistical evidence is strong. The training program significantly increased production rates for these workers.
Great news for the training department. Okay, let's move to comparing different groups. Part-time versus full-time students?
Scenario 7. A 2-sample t-test here. A newspaper claimed part-timers are older. Let's see. Sample 1. 42 part-time students, average age 26, standard deviation 2.
Okay.
Sample 2. 31 full-time students, average age 24, standard deviation 3.
So the part-timers are older in the samples. Is it significant?
Null hypothesis. Part-time average age, full-time average age. Alternative. Part-time average age, full-time average age.
Testing the newspaper's claim.
Right. The calculated t-statistic is about 3.22. Degrees of freedom are calculated using a formula. Comes out around 49.
And the p-value?
Very small again. About 0.000.
Less than 0.05.
Much less. Reject the null hypothesis. The evidence strongly supports the claim. Part-time students are, on average, significantly older than full-time students.
Looks like the newspaper was right on that one. How about tourist spending in the Bahamas?
Scenario 8. Another 2-sample t-test. Comparing spending on 2 islands. Grand Bahamas. Sample of 89 tourists. Average spend $2,860. Standard deviation, $126.
Okay.
New Providence. Sample of 64 tourists. Average spend $2,935. Standard deviation, $138.
So slightly higher average spend in New Providence in the samples. Is there a significant difference either way?
That's the question. Null hypothesis. Average spending is the same. Magidis mi MP.
Alternative.
Average spending is different. Magami UMP. Two-tailed test.
And the results?
The t-statistic is about minus 3.44. Degrees of freedom around 1 in 28. The p-value is very low, about 0.000079.
Less than 0.05 again.
Yes. Reject the null. There is a statistically significant difference in the average amount tourists spend on these 2 islands.
Interesting. Even though the difference looked relatively small, $75, it's statistically significant. Okay, next up. Salaries at 2 companies.
Scenario 9. Comparing Company A and Company B. This time, we'll assume we know the population standard deviations for salaries at both, so it's a 2-sample z-test.
Okay.
Company A sample of 72 employees, average salary $48K, population sigma $12K. Company B sample of 50 employees, average salary $43K, population sigma $10.
Quite a difference in the sample averages, $5. Is it significant?
Null hypothesis. Average salaries are equal. Alternative, average salaries are not equal.
Calculation.
The z-statistic is 2.5.
2.5 again. We saw that before.
We did. And the p-value for a 2-tailed test with z20 2.5 is about 0.012.
0.012. Less than 0.05.
Correct. Reject the null hypothesis. There is a statistically significant difference in average salaries between Company A and Company B.
Good to know if you're job hunting. How about student grades, UTC versus GSU?
Scenario 10. Another 2-sample t-test. The dean, UTC, claims their average GPA is higher than GSU's.
A bold claim. Let's see the data.
UTC sample of 14 students mean GPA 2.85, standard deviation 0.40. GSU sample of 12 students mean GPA 2.61, standard deviation 0.35.
UTC is higher in the sample. Is it enough? No. UTC GPA court GSU GPA. Alternative, UTC GPA, GSU GPA.
Right. Now, this one gives slightly different results depending on assumptions about variance. If we assume unequal variances, it is about 1.63. P-value is about 0.058. If we assume equal variances, it is about 1.61. P-value is about 0.060.
Both p-values are just slightly above 0.05, but it says test at a 10% significance level.
Good catch. So alpha is 0.10 here, and both 0.058 and 0.060 are less than 0.10.
So at the 10% level, we reject the null.
Exactly. At the 10% significance level, we reject the null. There's enough evidence, just barely you might say, to support the dean's claim that UTC's average GPA is higher than GSU's.
Shows how the chosen significance level can change the conclusion. Okay, moving on to tests about proportions, like that soft drink taste test.
Yes, scenario 11, a one-sample proportion test. New soft drink, 400 people tasted it, 100 liked it. That's 25% in the sample.
Okay, 100 out of 400, 25%.
The company wants to know, will more than 21% of the whole population like it?
So null hypothesis. Population proportion, P, is 0.21 or less. Alternative, P is greater than 0.21.
Correct. This can be done using a chi-squared test framework as well. The calculated chi-squared statistic is about 3.86. With 1 degree of freedom, the p-value is about 0.025.
0.025. That's less than 0.05.
It is. Reject the null hypothesis. There is significant evidence to suggest that, yes, more than 21% of the population will likely enjoy this new drink. Good news for the company.
It's like a potential winner. How about comparing proportions in two different groups, like voters in Alabama and Mississippi?
Scenario 12, two-sample proportion test. Alabama. 800 surveyed, 440 favored the Democrat, that's 55%. Mississippi, 600 surveyed, 360 favored the Democrat, that's 60%.
So 55% is 60%. Was the support level the same, statistically speaking?
No hypothesis. Proportions are equal, pal equal p miss. Alternative. Proportions are different, pal p miss.
And the chi-squared test result?
The chi-squared statistic is 3.5. With 1 degree of freedom, the p-value is about 0.061.
0.061. That's just slightly above 0.05.
It is. So we do not reject the null hypothesis at the 5% level.
Meaning?
We don't have enough evidence to say the proportions were significantly different. The 60% difference observed in the samples could plausibly be due to random chance.
Interesting. Close, but not quite statistically significant. Now, testing variance, like pipe length.
Scenario 13. A chi-squared test for variance. Pipes should average 16 inches. With an acceptable variance of 0.3 inches squared.
Okay, target variance is 0.3.
A sample of 25 pipes is taken, and their variance is calculated to be 0.4. Is the true population variance significantly different from the target of 0.3?
No. Variance equal 0.3. Alternative. Variance equal 3.
The chi-squared statistic is 32. With N25, we have 24 degrees of freedom. The p-value is about 0.254.
0.254 is quite large compared to 0.05.
It is. We fail to reject the null hypothesis. There's no significant evidence here to say the true variance is different from the acceptable 0.3. The sample result is within the expected range of random variation. The manual also gives a 95% confidence interval for the variance 0.24 to 0.77, which clearly contains 0.3.
Reassuring for their quality control then. Okay, what about university majors? Have the proportions changed?
Scenario 14. Chi-squared goodness of fit test. We're comparing this year's student distribution to last year's known proportions.
Right. Accounting was 30%, management 24%, marketing 26%, economics 20%.
And this year's sample of 300 students had counts. 83 ACT, 68 Milligate Merity, 85 Illigero Nitre, 64 Econ. Does this distribution fit the old pattern?
No, the proportions are still the same as last year. Alternative, at least one proportion has changed.
The chi-squared calculation gives a statistic of 1.66. With 4 categories, we have 3 degrees of freedom.
And the p-value?
It's about 0.646.
Very high.
Very. We definitely do not reject the null hypothesis. There's no evidence of a significant shift in the popularity of these majors compared to last year. The numbers look stable.
Seems like business majors are sticking to their patterns. How about employee resignations? Are they spread evenly through the year?
Scenario 15. Another goodness of fit test. We have 60 resignations last year. Winter 10, spring 22, summer 19, fall 9.
Spring and summer look higher. Is it uniform or not?
Null hypothesis. Resignations are uniform, so expect 604 equals 15 per season. Alternative. Resignations are not uniform.
The chi-squared test.
The statistic is 8.4. With 4 seasons, that's 3 degrees of freedom. The p-value is about 0.038.
0.038. That's less than 0.05.
It is. We reject the null hypothesis. The evidence suggests resignations are not uniform across the seasons. Spring and summer do seem higher.
That could be useful info for HR. Okay, is field of study related to gender?
Scenario 16. A chi-squared test of independence. We have counts of males and females in medicine, business, and engineering.
The numbers were medicine 80M 40F, business 60M 20F, engineering 160M 40F.
The question, is the choice of field independent of gender? No. Yes, they are independent. Alternative, no, they are dependent. There's an association.
Chi-squared calculation.
Statistic is about 7.11. Degrees of freedom calculation gives 2. The p-value is about 0.029, testing at 10% significance here.
0.029 is less than a 0.10.
Correct. Reject the null hypothesis. There is evidence of an association between gender and field of study in this data. They are not independent.
Okay, now comparing variability night shift versus day shift output.
Scenario 17. Using an F-test to compare two variances. Night shift N9 had variance 38. Day shift N8 had variance 20. Suggestion. Night shift is more variable.
So null. Var night, var day. Alternative. Var night, var day.
The F statistic is calculated as the ratio of the larger variance to the smaller one. But since the alternative is specifically night day, we put night variance on top. F is 3820, 1.9.
F 1.9. Degrees of freedom.
Numerator DF is N night 1 equals 8. Denominator DF is N day 1 equals 7.
Got the p-value.
The p-value for F 1.9 with 8 and 7 DF is about 0.206.
0.206, much higher than 0.05.
Right. Failed to reject the null. We don't have enough evidence to say the night shift output is significantly more variable than the day shift.
Okay, so the suggestion isn't supported statistically. Next, comparing means of more than two groups. Tire brands.
Exactly. Scenario 18. This calls for ANOVA analysis of variance. We have 3 tire brands, A, B, C, 10 tires tested for each.
Means were A 37K, B 38K, C 43K miles. Variances were 3, 4, 2, respectively.
Question. Are the average mileages the same for all 3 brands? Null. Mu A equals mub. Mu A mo nu. Alternative. At least one mean is different.
And the ANOVA result.
The dev statistic is very large.
Yeah.
23.33. The p-value is incredibly small, like 0.000000013.
Wow. Definitely reject the null.
Absolutely. There's very strong evidence that the average mileage is not the same across all 3 brands.
Okay, so ANOVA tells us there's a difference somewhere. How do we know which brands differ, like in the productivity program example?
Perfect lead-in to scenario 19. 4 productivity programs, A, B, C, D. 5 employees each. We record their productivity.
Goal. Is there a difference in average productivity, and if so, where?
First, the ANOVA. Null. All program means are equal. Alternative. At least one is different. The ANOVA F statistic is 6.14, and the p-value is 0.0056.
Less than 0.05, so reject the null. There is a difference somewhere.
Exactly. Now, we need a post hoc test, like Fisher's LSD mentioned here, to do pairwise comparisons and see which means are significantly different from each other.
And what did Fisher's LSD show?
It revealed that Program C, which had the highest average, 190, was significantly different from Program A, mean 145, Program B, mean 135, and Program D, mean 150.
But A, B, and D weren't significantly different from each other.
Correct. So the conclusion is Program C significantly boosts productivity compared to the other 3, which are statistically similar to each other.
Very informative. Okay, last one. Books, pages, and price related.
Scenario 20. Looking at 7 books, we have their page count and price. Question. Is there a relationship? Can page count help predict price? This uses regression analysis.
Null. No relationship. Pages don't influence price. Alternative. There is a relationship.
We look at the output. The overall ANOVA for the regression gives an F statistic of 6.44 with the p-value of 0.052. The specific test for the pages coefficient gives a t-value of 2.54, also with a p-value of 0.052.
Okay, p-value 0.052. It says test at 1% significance, alpha 0.01.
Right, and 0.052 is much larger than 0.01.
So we fail to reject the null at this strict level.
Correct. At the 1% significance level, we don't have evidence from this small sample to conclude there's a statistically significant linear relationship between the number of pages and the price of these books. Maybe other factors are more important, or the relationship isn't linear, or we just need more data.
Wow, okay. That was quite a journey through hypothesis testing. We've seen it used for averages, proportions, variances, comparing groups, checking relationships.
It really is incredibly versatile, isn't it?
Yeah.
And you see how it provides that structured way to evaluate claims using data rather than just intuition.
Yeah, it forces you to define what you're testing, look at the evidence, and decide based on probability, essentially.
Exactly. Understand that core logic, the null, the alternative, the p-value, the significance level. It's a powerful tool for thinking critically.
Absolutely. So for you listening, maybe think about this. Where in your own life or work do you encounter claims or make observations?
Right.
Could you apply this kind of thinking, even if you don't run the numbers, just framing it as, what's the baseline assumption, the null? What's the alternative claim? What evidence would convince you?
It's a useful mental framework, isn't it? Helps you assess information more clearly and maybe make more informed decisions.
Definitely. Something to mull over.